welcome back. Here we are talking now about changes that have been observed in the cryosphere. Now again, that word cryosphere is something that students often have forgotten. I mean, almost certainly at some point, like a high school earth science class or something like that, told you the word cryosphere. But just to remember, the National Ocean Service had such a simple definition of the word cryosphere. It's just the cryosphere is the frozen water part of the Earth system. This is going to be glaciers, ice caps, sea ice, even things like snowpack and so on, all count as what we call part of the cryosphere. And to talk first about, when we're talking about the cryosphere, let's start with talking about glaciers, because glaciers are awesome. We know what glaciers are. Glaciers are these things that up in the mountains, these kind of rivers of ice. We'll talk about them in just a little bit more, but just kind of set the question up here a little bit. I mean, it would make sense that if our world is warming, we would have fewer glaciers, or shorter glaciers, or smaller glaciers, or slower glaciers. Or I'm not quite sure now that I think about it. I'm not sure what to think about glaciers. Let's be clear about how glaciers work. Glaciers form in cold places where the snow that falls during the winter does not completely melt in the summer. And so there is an accumulation from one year to the next of more and more snow on the ground. And the weight of that snow kind of crushes the snow at the bottom, making a kind of a type of ice. Not exactly the same as like ice from your freezer. It's crushed, packed snow, and it can flow a little bit. So typically up at the top of the glacier, there's some kind of reservoir of ice, like, you know, the top of a mountain or an ice field or something like that at some high elevation maybe. And then its own weight has crushed the ice, and the ice actually begins to flow down the valleys. This crushed ice, crushed snow, it kind of can flow a little bit like a liquid, although, I mean, it's a very, very slow flow, you know, on the order of like feet per year or something like that. And so I thought I'd show you some pictures. A few years ago, my wife and I took a vacation to the Canadian Rockies to go see some glaciers while there still are glaciers. And that's me without a beard up on a glacier there, riding the Ice Explorer to the Columbia ice fields. I'll show you more pictures of these vehicles in just a moment here. But so we went up to these glaciers here, which were really amazing. We're really quite high up in the Canadian Rockies on the Columbia ice field, and you know, the Columbia ice field accumulates more and more massive snow each year, which crushes the snow at the bottom of the field into this ice, and then it kind of gets extruded out down the valleys. Here's the vehicle that we were in wasn't quite this old, but this is the kind of ice cat that carries people up to these glaciers and so on, because it can drive first on the gravel and then on the glaciers, which can't be good for the glaciers. It can't be good to be driving vehicles on glaciers, but whatever, we went with them and we took the tour. And like here you can actually see a glacier coming down the mountain. If our eyes were sensitive enough to tell that this thing is moving, we would see that this thing is tumbling down the mountain. But of course it's tumbling down the mountain relatively slowly, like a few meters per year. But more and more snow each year accumulates at the top of the mountain, pushes this thing down the mountain. Meanwhile, on the leading edge of this glacier, there's melting. Now, if everything is in balance, just as much snow is depositing up at the top of the glacier as water is melting off the bottom of the glacier, and the leading edge of the glacier stays still. But of course, during colder climate periods, the glaciers don't melt as much at the bottom as they accumulate snow at the top, and the glacier gets longer and extends farther down the valley. And during warming periods, there's more melting at the lower altitude parts of the glacier down near the leading edge. Then there is accumulation of snow at the top, and so the glacier gets shorter and shorter. And these glaciers are, you know, commonly seen at high altitudes in the mountains. Now we think of them as like you go to Canada or you go to Alaska to see them, but there's nothing explicitly about the fact that it has to be up in Canada or Alaska at some high latitude location to see them. There's plenty of glaciers in the tropics. Tropical glaciology is a real thing. You can go get books and journals and stuff about. You can be an expert in tropical glaciers. There are plenty of glaciers at the equator. As long as the mountain is high enough that there's snow at the top of it, there's no reason you can't have glaciers in any part of the world. But We went to Canada to see them some number of years ago. And a zillion people were with us, by the way. We had this idea from like the website that you'll be out on the glaciers. You'll be the last to catch a glimpse of them before they melt, kind of thing. And oh heck, there were busloads of tourists out there. We had no idea. Anyway, so yeah, so those are just some pictures from a vacation we took some years ago. Glaciers turn out not to be all that hard to monitor because, I mean, the fundamental property of them that's important is how long they are. And long, how far something extends into the valley, heavens, we've been measured, that's easy to measure. So we can measure the length of a glacier pretty easily. Now, like for example, this chart from your textbook shows you how the lengths of glaciers have been changing since the 1700s. And it's averaged over all the glaciers that are monitored in North America and South America, the Southern Hemisphere, the Alps, the North Atlantic, etc. I don't remember exactly. I think your textbook actually, provides references to how you could actually find out what glaciers were included and how they did this and so on. But they defined the length of the glacier at 1950 as 0, and you can see that prior to 1950, all these regions, the glaciers were longer than that, by an average of about a kilometer to a kilometer and a half. And since 1950, all the glaciers are shorter than this. In fact, I believe your textbook actually says that only one glacier in that study hadn't gotten shorter in that time period. Well, that's a sign that something's not in balance. Now, it is true that temperature is not the only factor that controls how long a glacier is. I mean, things, for example, like the amount of precipitation. Maybe what's changed is there's not as much snow at the top of the mountain anymore. That's certainly possible. Maybe what's changed is cloud cover. Like, it used to be cloudier and cooler over those locations, and now it's sunnier and warmer and they're melting. Oh yeah, that's absolutely possible. There's no doubt about that. So we better find out how we can decide that it's the temperature and not the precipitation and the cloud cover and so on. Well, being as all the glaciers in all these domains were deteriorating, their lengths were decreasing, except, I mean, there was one that had surged. Clearly, whatever is causing these changes to the glaciers is a global phenomenon. If all these glaciers in all these different parts of the world are all doing the same thing, it would be a remarkable coincidence if, like, oh, the glaciers in North America are retreating because of this, but the glaciers in the Alps are retreating because of this, and the glaciers in Scandinavia are decreasing because of this. That would be weird. There's all these different reasons, but it all worked out to the same answer. That would be odd. That doesn't sound like science. So there must be a global reason. And one global reason that things are going on is we know the planet is getting warmer. On the other hand, there is no global trend in things like the amount of precipitation the world is getting, or the amount of cloud cover that the planet is observing. So, some glaciers are in the tropics, where maybe they're getting more rain. Some glaciers are in subtropical latitudes, where maybe they're getting less rain, or snowfall, or whatever. But if all these regions are seeing the glaciers are getting shorter, then it has to be a common reason, and the most scientifically plausible reason is the observed global warming. How about sea ice? Okay, sea ice is this layer of ice that can form over very cold oceans. Sea ice is water that freezes at the top of the ocean to form a layer of ice that floats on the top. And sea ice is not particularly thick. Sea ice is on the order of, midwinter, hard frozen sea ice might be a few meters thick at most. Okay, there's still an ocean underneath there. Whales are swimming by. The Russians are taking their submarines under this. Whatever. Americans are taking their submarines under it. And then there's a relatively thin crust, a few meters of ice up on top of there, floating on top of the ocean. And the amount of the Arctic Ocean that is covered by this kinds of sea ice really has a huge annual cycle. There is a very, very big difference between the amount of ice in the warm season and the amount of ice in the cold season, and fortunately that turns out to be one of the easiest things out there to monitor using satellites. Most meteorological and climatological satellites have a polar orbit, which means every 90 minutes they pass over the North Pole and the South Pole, which means they got their cameras out there and they have different kinds of imagers and so on, and they can all kinds of sensors that can measure the thickness of the ice and the extent of the ice and even like the age of the ice to tell what's new ice versus what has been there, multi-year ice. All that can be very easily monitored by satellites. And just to give you an example of this very large annual cycle, this is two plots I got from the National Snow and Ice Data Center, which is a thing that exists. And I can't remember if this is 2013 or 2015 or whatever, but anyway, it was some year I got the comparison between March, which is about the time of year with the maximum sea ice extent, and September, which is about the time of year with the least sea ice extent in the Arctic. And of course you can see that in March, when the sun hasn't even been up in the Arctic for months, the sea ice extent is huge. It extends down into Hudson's Bay and down into Bering Sea, all through Scandinavia and northern Russia, and yeah, Greenland. All these places are frozen in sea ice. Whereas like in September, when the sun has been up for months straight, 24 hours of sunlight for months up there in the Arctic, the sea ice extent is very, very small. There's open ocean alarmingly close to the North Pole. You can actually sail all the way around northern Russia and along much of the northern coast of Alaska and so on. Okay, so we can see where the sea ice distribution is, and we can see that there's this huge annual cycle to the amount of sea ice. It's going to be hard to describe the average amount of sea ice because there's just so much variability. Where are we going to be looking then for changes in the amount of sea ice? Well, I wouldn't look for it in the winter. Don't get me wrong, there might be less sea ice in the winter now than there used to be before global warming and so on. But see, here's the deal. The Arctic is so far below the melting point of ice in the winter that even if the climate is a few degrees warmer, heavens, even if the climate is a great deal warmer than usual in the winter, you're not going to get all that close to the melting point. And so realistically, it's not going to change that much. It might be a lot warmer than normal, but it's still below 32 degrees Fahrenheit, 0 degrees Celsius, so there isn't going to really be all that much change in the amount of sea ice at like the North Pole in the winter. On the other hand, at like summer, like in September, at the end of the long summer, the temperatures are pretty much right around the melting point, right around 0 degrees Celsius. A little bit of warming means we are now above the melting point, and there's going to be a lot more melting going on. A little less warming means we didn't get above the melting point. It isn't like when the temperatures are just a little bit below melting, we get a little bit of melting. No, if you don't get above 0 degrees Celsius, you don't have any melting. So it looks like September would be a good month of the year to be trying to study, because it seems like that would indicate very easily if warming is happening or not. If warming is happening, we're going to be having a lot of deterioration in the warm season, like in September. And so, for example, that happens to be what is sort of the standard in the field of studying sea ice. Here is the average extent of sea ice in the Arctic as monitored by satellites from the National Snow and Ice Data Center. And you can see that the scale's a little goofy. Notice it doesn't go all the way down to 0. It's just from 8 to 4 million square kilometers. But you can see that in the period of which we've been having satellites monitor the polar regions, from about 1978 or 79 to the present, you can see that there's been a fairly alarming trend in the amount of sea ice every September. There's still quite a bit of variability from year to year, but some of this has not been good at all. Sea ice deterioration is bad news. Yes, it does not change sea level, but it is more than just an indicator of climate change. It isn't like somehow or other this is our scorecard. Oh, we've got sea ice change decreasing. That's another piece of evidence that the planet is warming. Well, yes, but more importantly, sea ice is part of the story about how the planet is warming. See, sea ice acts kind of like a blanket between the relatively warm Arctic Ocean and the bitterly cold air. Let me give you an example. Look at the picture I have there in the background. See how there's pretty much continuous coverage of sea ice over the surface of the ocean there? And actually I only chose that picture because it was fairly dramatic. I mean, when the sea ice completely covers the ocean, it just looks white. It wasn't a very interesting background. So here, just a few meters below the surface of this ice, there's ocean water. And it can't be colder than 0 degrees Celsius or it would be ice too. If there's open water that's full of whales and Russian submarines and stuff down there, the temperature of that cannot be colder than 0 degrees Celsius, which is pretty cold, but is way, way warm compared to the air on top of there. I mean, the air temperature is at the North Pole, 40, 50 degrees Celsius below 0. So that layer of ice that's sitting on top of the ocean is like a blanket keeping the almost scaldingly hot Arctic Ocean, compared to the very cold, bitterly cold air on top of it, keeping them apart. And there's a nifty expression for that. There is a sensible heat flux. Heat flows from warm things to cold things. The technical term for that is a sensible heat flux. A flux, it's in motion, and it's sensible heat. You could measure it with a thermometer. That's in contrast, there's other forms of heat that aren't sensible heat. But this is as in we could measure it with a thermometer. Well, when there's a layer of ice covering the ocean, ice is a pretty good insulator. It keeps that relatively warm Arctic Ocean away from the bitterly cold air right above it. Just over that course of that few meters of that layer of ice is more than enough to keep there from being much of a flux of heat, of sensible heat, from the ocean up into the atmosphere. On the other hand, look at a situation like this, where the ice is all broken up and mostly melted away and so on, and we could even think of situations where maybe all of the pack ice had melted. Well, without that ice coverage, heat can freely conduct up from the relatively warm ocean into the bitterly cold air, making the air less cold. Okay? There is a sensible heat flux here, a flux or a flow of sensible heat, like what you could measure with a thermometer, and it's huge. And so, whereas the air masses previously that were sitting on top of this ice sheet might have been 40, 50 degrees Celsius below zero, well, now huge amounts of heat is being added to this air. And, depending on how long the air mass sits on top of this open ocean, it might warm up all the way to 0 degrees Celsius. No matter what, it's going to experience a great deal of warming. This is our first little example of the kind of climate feedbacks that can happen. I mean, a warmer planet is making for less sea ice, and less sea ice makes it easier to warm up the air over the Arctic. This is a potentially disastrous feedback, and it's one of several feedbacks we're going to learn about when we learn more about the physics of climates. Okay, so far we've talked about glaciers, and we've talked about sea ice. How about another type of ice that's part of the cryosphere, like ice sheets? Big, continent-wide sheets of ice that bury, Antarctica and Greenland. Antarctica and Greenland are really the only parts of the Earth that at this time in Earth's history are covered with ice. With ice sheets. We know that other parts of the Earth have been covered with ice sheets at many times, including much of the United States in the last ice age, but at this point in Earth's history, the only parts of the Earth that are covered with true ice sheets are Antarctica and Greenland. Now, they are, in fact, the single largest store of fresh water on Earth, and in fact, if they completely melted away, they would increase the sea level of the Earth by 100 meters. There's a lot of ice in Antarctica and Greenland. I don't know off the top of my head exactly how thick the ice sheets are in Greenland, but in Antarctica, they're several kilometers thick near the middle of the continent, near the South Pole. I mean, that is an enormous volume of ice. And like, for example, we can monitor the mass of the ice that is on these ice sheets. Here is, for example, the trend that we're seeing in ice for Greenland over the last, what do we got here, about 7 or 8 years. And they're just keeping track of changes in the mass of the Greenland ice sheet in units of gigatons, billions of tons of ice. And you can see that since about 2002 to about 2009, over that period of record, the Greenland lost 1,600 gigatons, which would be, 1.6 trillion tons of ice. Whoa. Wait a minute, how do we know that? I mean, I don't know what kind of instrument would be measuring the mass of an ice sheet. I mean, we can't exactly put Greenland up on a scale, right? Well, it turns out that there are elements of the Earth system that are so big and so heavy they affect the Earth's gravitational field. And the Greenland ice sheet is one of them. We have satellites up there in orbit, such as this one whose webpage I put up here. Its name is GRACE, the Gravity Recovery and Climate Experiment. And this satellite is tuned to very precisely notice changes it experiences in gravity as it orbits the Earth. And when it passes over certain gravitational anomalies, it feels itself moving, being drawn a little closer to the Earth, or being able to get a little bit higher away from the Earth. And it can determine from that things like the mass of different very large things, like a Greenland ice sheet. Or it can find out like the mass of snowpack up on top of a mountain. I mean, the mass of the mountain changes when there's more snowpack up on top of it. Or the mass of water behind a reservoir. Okay, if the reservoir is draining, as the satellite goes by, as GRACE goes by, it can feel that it is experiencing less gravity as it goes past this reservoir. And there are lots of applications in climate science to these kind of gravity recovery experiments. And that slide I showed you with the Greenland ice sheet stuff, actually, that did come from GRACE. And it can actually measure changes in the mass of the Greenland ice sheet. And we don't like the numbers that we're getting. Clearly, the Greenland ice sheet is deteriorating with respect to time. So the same is true of Antarctica. In fact, one of the big ice sheets in Antarctica, the West Antarctic ice sheet, is deteriorating very rapidly, and there's some reason to think that the leading edge of it is no longer touching the ground as it moves out over the ocean. It's not grounded on the bottom of the ocean anymore. It may be floating, and that would be very bad if relatively warm water is getting underneath the ice sheet now. Oh, that would be bad, bad news. But really, as we look across all this ocean and cryosphere evidence, what I really want you to notice is, above all else, it's the consistency of all these different sources of information. And that's what's giving us confidence that the warming that we saw in the previous lecture has to be real. There's no reason why Grace should be finding that the Greenland ice sheet is melting and sea ice is decreasing and deep ocean water temperatures are increasing and sea level heights are increasing, except for the fact that of the reality that the planet's surface is warming. Okay? That's really the only way that all these things could be happening. All these glaciers could be retreating, all these ice sheets could be deteriorating, etc. It's impressive to have such a collection of evidence that all says basically the same thing. What does the IPCC make of all of this? Okay, when we look at their assessment report, now I mainly had you just look at the executive summary of the ocean part. You're certainly welcome and encouraged to look through all the results, but just to kind of keep your reading assignments manageable and so on, I just had you look at the ocean part of the executive summary. And like, to use their exact words here, they said, it is virtually certain that the upper ocean above 700 meters has warmed from 1970 to 2010, and it is likely that it has warmed since the 1870s. Virtually certain, again, if you follow the footnote there, is their terminology. They decided virtually certain means 99 to 100% probability that this is true. Okay? Even the people who were skeptical and served on the IPCC came to an agreement that it is 99 to 100% certain that the planet's oceans from 700 meters on up have warmed since 1971. That's amazing, okay? And it is likely that it has warmed since the 1870s, okay? As the quality of the observations gets poorer and the number of observations gets poorer farther back, there's less confidence that the trend that they're seeing is real, but still likely that it is true. I don't remember exactly. I think likely is 66 to 100% agreement. 66 to 100% probability that it is true. Okay, so that is still pretty good evidence for the very long term, and the shorter term, since 1970, is a done deal. Another thing that happened to say in that executive summary, confidence for the time period since 1971 is high based on increased data coverage and the high level of agreement among independent observations. Confidence, remember, is a key word in the IPCC report. It is a way that they express the measure of agreement. Okay, there's very good confidence if people from a wide range of backgrounds and a wide range of expertise and a wide range of political opinions and so on and a wide range of different schools and all that kind of stuff, if they all are in agreement that that's what these facts mean, we can be very confident in that. It's less confident, we are less confident in a result if, like, the oceanographers tend to see it this way but the atmospheric scientists see it this way. Or scientists from Western nations interpret it this way, but scientists who were educated in Eastern schools tend to see it that way. That's complicated, and then it reduces the confidence in results. Our confidence is high that the ocean, the deep ocean, is warming based on the level of agreement and consensus and so on. It is very likely, furthermore, that the mean rate of global sea level change was 1.7 millimeters per year. That's a new unit for us, right? Okay, I mean, we talked about it in inches and stuff. But millimeters per year, that's real. Between 1901 and 2010, and that rate increased to 3.2 millimeters per year between 1993 and 2010. Again, very likely means that they think there's a 90 to 100% chance. Now, they actually provided a range in the text. It was like, the mean sea level change was 1.7 millimeters per year, and they were confident it was between 1.6 and 1.8 millimeters per year or something like that. And same with that other number, 3.2, there was a range. But there's a confidence, and it's 90 to 100% chance the actual rate of sea level change for the planet is in that range. That's very high agreement that the ocean is changing in that way. Wow. Lots of bad things have happened to our planet. We've seen lots of different kinds of evidence that the planet is warming. We can emphatically say that the planet is warming. We saw so many different kinds of evidence. what wouldn't count as evidence? I mean, surely not everything is bad, okay? What kinds of things don't count as evidence? That's what's going to happen in the next lecture. Before we move on then, the final lecture in this module is going to be about paleoclimate. But before we get to there, I want to ask a couple questions about this ice section. Just to make sure we're very clear about the whole thing about like glaciers and sea ice and so on. Question 3. Glaciers are found A, on icebergs, B, each winter across Nebraska, C, covering the Arctic Ocean, or D, on mountains. I hope that's not too hard of a question, but it could be that that is a new vocabulary word for you. Follow a link below this video to get some feedback on your answer before we move on to question 4.